All right, so this is on Computergraphics Part 1. Of maybe 4 or 5, depending how we spread this out. So what I want to talk about today, a couple things in this particular section, is to sort of talk about what the goal of this chapter is, and then talk a little bit about linearity, and they go well together, right? So the goal of this section is, in 2 and 3 dimensions, we'd like to look at points and how we can act on those points. So points can be represented by vectors, right? So in 2D and 3D, we can, I'm going to say can because this is going to get tweaked a bit, but we can represent points by vectors. So for example, the point 2, 5, this can be represented by the vector 2, 5. And say the point 1, -1, 5 in 3 dimensions can be represented by 1, -1, 5 like this. So that's particularly convenient. So what would be nice is if we could represent operations like translation and rotation by matrix multiplication. So we'll say it would be nice, and I'll explain why it would be nice if we could represent translations, so think shifts, and rotations by matrix multiplications. So for example, to translate, can we find a matrix? Let me bullet this so we see. Can we find a matrix T so that translating a point P can be done by doing TP. And for example, to rotate by some amount, don't worry about how much right now, can we find a matrix, say R, so that rotating a point P can be done by doing RP. Now we're also going to look at perspective projection, but I'm going to leave that for last. But what I do want to look at for right now is why would we? Like, why is this beneficial? So there are 3 primary reasons that we can look at. There are a bunch of reasons, but 3 main reasons. So reason A is matrix multiplication is computationally easy. That's the first thing. B, if we wanted to do 2 things in succession, we could just multiply matrices. So to, for example, let's say translate, then rotate, we just do T times P first, and then times R. That's the same as RTP, and that's also convenient. Because in other words, RT just does both of those things together. And C, the third thing is, typically when you're working with computer graphics, you're not working with 1 point at a time. So to do multiple points, say P1 through Pn, all we do is, for example, T, and we construct the matrix P1, Pn. Now, just so that you note, because this might be a little rusty, the definition of matrix multiplication, right? Not how we compute it by hand, but the very definition of, say, A, B from matrices A is, in fact, you take A and you multiply it by each column in B successively. So what that means is, if you want to, say, translate many points, you just put the points in a matrix and multiply by t. Right, so basically we can handle all the points at once. Right, so for example, if you had a bunch of points and you wanted to, I'll just put a little note in the middle here before we go on. If you had a bunch of points and you wanted to rotate and then translate, you could do something like this. Right, so you create a matrix of points, you rotate, and then you translate, and you get a nice result. So this is the reason why we want to do this. So the first thing we need to look at is to understand, like, is this possible? What's special about matrix multiplication? Things like this. So let me clear the screen, and then I'll sort of take a brief segue into the concept of linearity, and that'll bring us back to matrices. And then we can dig in and start doing calculations. So 2. So linearity. So just to remind you, you may have forgotten what it means for a function to be linear, right? So we'll say, suppose that f is a function from Rn to Rm. So then f is linear. This means that f of alpha u plus beta v, u and v bar, is alpha f of u plus beta f of v. This is for all u and v in Rn, and all alpha and beta in the real numbers. So most functions are not linear, right? So for example, f of x is x squared is not linear, because in general, for example, f of x plus y is different than f of x plus f of y. Right? In general, x plus y squared is not the same as x squared plus y squared. Sometimes it is, but to be linear, this sort of thing has to be true for every single possible x and y. Or for example, whereas for example, the function f of x, let me write this as a vector, so we're sort of back in home territory. F of xy is, say, 2x and then x plus 3y. This is linear. And you can check this just by doing a calculation. It's not the most pleasant calculation in the world, but it's not bad, right? So if we look at something like f of alpha x1 y1 plus beta x2 y2, if we look at that linear combination, so this becomes, this is not so pleasant. This is f of alpha x1 plus beta x2. I need to combine these. And then I can apply the actual function. So the actual function says the top entry is 2 times x. That's 2 times alpha times x1 plus beta times x2. And the bottom is x plus 3y. So that's alpha x1 plus beta x2 plus 3 times the y, which is alpha y1 plus beta y2. This, of course, because this is just a vector now, this can be split back up. So I can write this as follows. I can write the first part, so I'm going to take the alpha and I'm going to write everything that has an alpha in it. So 2x1. And in the bottom, I'm going to write everything that has an alpha in it. So x1 plus 3y1. And then separately, everything that has a beta. And downstairs, everything that has a beta. And this, of course, is the same as alpha f of x1, y1 plus beta f of x2, y2. And because these are the same, so if you look at these two things, this one and this one, these are identical. Therefore linear. In other words, this function right here is linear because this is true. So there's a big theorem from linear algebra, which I won't prove. We don't worry about the proof right now. You can check it, you can look it up, you can look at any linear algebra book talks about this. This is the classic useful thing, is that a function from Rn to Rm is linear if and only if it can be represented by matrix multiplication. So I'll remind you of what that means. In other words, that is, so there exists a matrix. This would be an m by n matrix such that f of u is mu. So if you can find a matrix, or rather f will be linear if it is possible to find a matrix such that this works, right? And moreover, if this is the case, in other words, if it is linear, then we know what that matrix is. It turns out that this matrix is just constructed by applying f to the basis vectors. So remember, E1 is a vector with a 1 in the first entry and 0 is everywhere else. And E2 is a vector with a 1 in the second entry, and so on. So, for example, what I'll do is this: I'll clear the screen and then I'll re-mention our linear example, and then we'll write down the matrix for it. So, for example, we saw that this function is linear, and so we can construct the matrix for it. So the matrix will be constructed by taking, what I'll do is I'll do f of 1, 0, I'll do f of 0, 1, I'll jam those together in a matrix. So f of 1, 0, put 1 in the x and 0 in the y, so I get 2, 1, oops, not. So that's this one, and f of 0, 1 is 0, 3, that's this one. So in other words, we could rewrite f by doing that matrix times xy. And this is convenient. So this takes us back where we were, right? What we were saying is we wanted to represent rotations and translations and perspective projections we commented on by matrix multiplication. So what that means is they need to be linear, right? So here's the deal. In order to represent translations rotations, and I'll mention this now, and perspective projections. I'll say more about those when we get there. By matrix multiplication, they need to be linear. Once we know that they are, then we can find the matrix. So once we establish this, we simply find the associated matrices. So I'm going to stop there for this video, keep it nice and brief, except to say that that will be our job, right? So what we'll do next is we'll look at translations and we'll say, hey, are they linear? If they are, let's write down a matrix. Look at a rotation, say, is it linear? If it is, we write down a matrix. Perspective projection, is it linear? If so, write down a matrix. Now, it's not so simple. We're going to run into some problems, but we can patch those up as we go along, and we can see that everything will work out nice.